pleasure to have Corin Jorgenson speaking with us from Geneva, Switzerland. So Corin actually originally from Canada and got her degree in Tallahassee, I think, before she moved to her current institution working on her PhD thesis. I think this is just one application that you have worked it out, but I think it's quite interesting. So with that, I'll give it the right time to Corin. And normally our talks around about 40-45 minutes, and then later for another 15 minutes for interaction with our participants. So please, Corin.
Great. Thanks everyone for coming and for having me, and thanks also for being here at 8 p.m. for I think lots of you guys, which for me is late, but I'm happy that you're here. So today I'm going to talk to you guys a little bit about a machine learning approach to thermobarometry, specifically clinopyroxene thermobarometry. And of course, this is because I just published a paper last year with the rest of my lab group on it in JGR. So of course, I'll explain it now and happy to answer any questions, but there's obviously more detail in the paper if it's something you're interested in. Okay, so today, what I'm going to do is I'm going to explain a little bit about the idea behind what thermobarometry is, then talk about how the machine learning aspect of it works, some of the things that we need to consider looking at our model, and then a few applications, and then we'll end off with how you can access it if it's something that you're interested in. Okay, so what is thermobarometry? Well, of course, thermobarometry is the study of pressure and temperature, but in our case, we're looking specifically at the pressure and temperature of crystallization of a mineral. And we are looking at clinopyroxene as our mineral. And this is helpful for us because this helps us to understand the architecture and the plumbing systems of volcanic and igneous systems. Now, I do volcanology, so the volcanic side of it is of course really important for me, and it's something that I think is a really powerful tool, especially if you use it with stratigraphic data as well, because you can get a temporal evolution of how things are changing with time, and you can maybe even try and figure out how this could lead to an eventual eruption. How does this work on a more like mineral side of things? Well, you all probably know that minerals have a distinct lattice structure that's repeating. So if we take the example of clinopyroxene, do my little laser pointer, you can see this is like the formula of clinopyroxene. I'm sure you're all familiar with it. And it has these two M sites. Now, the volume that these M sites take up is inversely proportional to the pressure that you might remember from like high school chemistry. The PV equals nRT, pressure and volume are inversely proportional. So when you increase the pressure, you decrease the volume that these M sites can take up. And when you decrease that volume, you're going to preferentially get smaller elements in these sites. Now we can use this information to figure out some things about pressure and of course temperature as well. Okay. There's lots of actually thermobarometers out there, and there's lots of clinopyroxene thermobarometers out there too. Now, some of them are super great, and some of them also have some things to think about. So one of the things that you always need to think about with the thermobarometer is what it's calibrated on. So what pressure, temperature, and compositions are appropriate for this thermobarometer. And it's not always really easy to know what works really well for each thermobarometer, but it's something that's really important to know. And because of this, there's not always a good option for all different types of melts, especially there's not really any good options for mafic and alkaline melts, which is what I look at, but also for really alkaline, even like more intermediate melts. There's not great options for that. Additionally, some early versions of thermobarometers, the error was calculated in a way that wasn't the best. They often used the test data set or the training data set as the testing data set so that they were getting errors that were much lower than they actually should have been. Now, of course, the like more updated thermobarometers, they don't do that anymore, but this is something to keep in mind that whenever using a thermobarometer, just to think of these kind of things. Now, we decided to turn to machine learning. You can see this nice little cartoon that does not explain what machine learning it is, but it's fun. So some of the great things about machine learning is, first of all, that it's data-driven. We're not using any assumptions in advance. We're really just looking at the data and looking at what the data tells us. Additionally, it allows for us to use a wider range of compositions. We can choose what we put in the data set, and then that helps tell us what we can use it for. It's customizable and it's dynamic, meaning that this is something that that users can use, and they can change and shift, and it's something that can evolve with time as we get more information quite easily. Lastly, we have a robust error assessment, and we have a way to have individual uncertainty estimates, which is a great thing, I think. Okay, so enough about the machine learning. What kind of machine learning are we using? Okay, so we're using a machine learning technique called random forest, specifically actually using one called extra trees, which is a type of random forest. Now, the reason why we're doing this is because we found this nice study from Petrelli et al. 2020, and you guys, I think some of you just had a course with him a few weeks ago from Maurizio Petrelli, and so he tested a lot of these different machine learning methods for clinopyroxene thermobarometry, and he found extra trees is the best one. And so me and the rest of my lab group all found this, and we got the code from Maurizio, and we were like, this is amazing. Except for we all started doing some different things. Some of us would use different number of trees. Some of us were using different calibration data sets. So we decided to all come together along with Maurizio and just make this nice methodology that everyone can compare their data from, so that we're not comparing different methods, but instead comparing actually different results, so that we have some good science to talk about. Okay, so what is a random forest? So essentially what a random forest is doing is you're taking a calibration data set, you're giving it to an algorithm, and you're saying, okay, I want you to figure out how to determine the pressure from this data set. And so the algorithm takes that and it does this, making things called decision trees. Now, what is our calibration data set? So in our case, our calibration data set is clinopyroxenes that are made in a lab setting. So it's an experimental clinopyroxenes. These are made with like a piston cylinder apparatus or whatever apparatus the experimental petrologists use. And we collected these from the Library of Experimental Petrology Research, but of course updated that because it hasn't been updated in a few years. So this is all of the data that we have in our calibration data set. This is the melt that these clinopyroxenes originated from. As you can see, it spans quite a wide range of silica content, and we are getting even some of these alkaline compositions, which is great too. Okay, so we take this calibration data set and we give it to the model, and it puts it into a decision tree. Now, what is the decision tree? Okay, so you see there's a fun little example of a decision tree. It's basically a hierarchical flow chart. So we can go through this one. Did you do some science today? Yes or no? I assume yes for all of you. Was the science good? Yes or no? Let's say it was. You deserve some chocolate and you should eat some chocolate. It's a great decision tree. Basically, you're just asking a bunch of yes or no questions until you get to an outcome. In this case, it's the best outcome is that you get to eat some chocolate. Now with our decision tree, so they're not quite so simple. Instead of answering these yes or no questions, we're splitting our data left and right on the basis of mineral chemistry. So we can see it's like simplified version of a decision tree here. We can split left and right on the basis of the sodium content. So everything, let's say above, I don't know, 2-8% sodium goes to one side and everything else goes to the other. Then we can split again at calcium, magnesium, and you just keep splitting and splitting and splitting until you can't split the data set anymore, and then you've arrived at a pressure. So that's how you make one decision tree. And then you can apply that to natural data, which of course you don't know the pressure, but you do know the mineral composition. And then you can just follow through the decision tree right here until you get to the desired pressure. Now, if we split at, say, silica first instead of sodium, or we split at sodium at 2-8% or 4-8%, we're going to get a different decision tree. The decision tree is going to look a little bit different. It's going to have a different structure to it. And that's why it's a random forest. It's comprised of many, many decision trees. And then we can take the results from all of these decision trees, and then we get some nice like little histogram, and we can use some counting statistics to try and figure out what's the best pressure. And I'll talk about that a little bit more later on. That's the principle. That's the idea of basically how random forest works. In reality, there's a few other things that we want to think about. So some of these are hyperparameters, how we look at the errors, and then the voting distribution. So we'll go through all of those right now. So hyperparameters. You can think of hyperparameters as things that you adjust in the model. It's not something that will drastically change your model, but if you tune them all the right way, you can get your model to run just a little bit better. So now there's lots of hyperparameters to consider, but we'll just talk about two of the main and most important ones. So the first one is the N tree, or the number of trees. And this is basically just asking how many trees are in the forest. The next one is M trie. So this one is a little bit harder to explain. The easiest way to say is just it's what and where to split. And I think the easiest way to look at the M trie is just to give you an example of one. So we'll go through one now. So we'll start with, let's say we have our calibration data set at this point has 8 points, and we have an M trie of 6. So when we have an M trie of 6, the model is going to randomly choose 6 elements, and it's going to randomly choose a split point for each of these 6 elements. So then it's going to take these elements and it's going to calculate the score for each of them. So it's going to calculate the score, and the score is based off of the variance. So this is the equation that it uses. It takes the weighted variance of what everything is split on the left and off to the right of this element. So we can look with silica. We can see this worked example. We have 8 points. So these are our points, and this is where the split is. And then everything on the left, we can calculate the variance of. Everything on the right, we can see here, we calculated the variance of it. And then we can calculate the score to get the final score for the silica. Now you can repeat that for each of these 6 elements. And then the model knows that the one with the highest score is the best one to choose for the next node. That's what the M trie is. The M trie is essentially telling you how many times how many elements you should pull out of a grab bag. In this case, it's 6, but you could have had 8, you could have had 2. So this is, it's basically choosing how random or unrandom a little bit you want it to be. So basically how many times you reach into that grab bag. And remember, each time it grabs something, it gets a new split location. So even if it grabs magnesium twice, these will have different scores because they'll be splitting at a different spot. Okay, so that's the M trie. Now we can take a look at them and try to see how we can standardize them to make sure that my model and your model is doing the same things and is working the best it can. So we can take a look at the M trie first, because what we just discussed. And so on this x-axis, we have the mean standard error estimate. This is just a way that we can see how well it's performing. So it's our error essentially. And on the y-axis, this is our M trie. It's color coded for different numbers of trees, but for now you can ignore that and just look at the blue color. So as you can see, when we have low number of M trie, it doesn't do so great. It's 4 kilobars. But if we increase that, it slowly starts to get better. But at a certain point, right around 6, it doesn't seem to get that much better when you increase. In fact, it starts to steady out. Now, as we just saw, the M trie, when you increase the number of M tries, you increase the number of calculations you're doing. So this is where you kind of have to think about a little bit of a balance of how much computational time you want to take up versus whether or not that actually makes your model better. So we decided in this case, increasing the M trie to like say 7 increases our computational time, but doesn't actually really make our model that much better. So it's not really worth it. So we decided in this case, the best M trie would be 6. But actually, if you increase the number of M tries, if you increase your number of total variables, let's say we doubled this, like if you had liquid data, this curve stays the same. So actually, in fact, the best number of M trie is 2/3 the number of variables. Okay, now we can take a look at the N tree. How many trees do we want in our forest? Now, once again, these are color coded for the M trie, so you can ignore it and just look at this one, this like nice kind of dusty blue color. If we have 100 trees, it does okay. 200 gets better. 300, it's still the same. 400, it goes over back to be a little bit worse, and then it kind of splits around. So this is another instance where we can kind of play that judgment call of whether or not increasing the number of trees is actually going to make it better or not. And in this case, we think it won't, because we can see from our models it's a bit unstable. So the best thing to do is just to use 200 trees. And this is actually quite consistent with the literature, the machine learning literature. They usually find the best number of trees to be somewhere between 100 and 200. So we just choose 200 as our number of trees, and that's the same no matter how many variables that you have it. So it's the same if you only have clinopyroxene data or if you also include the liquid data. So these are the hyperparameters that we like. We think they're the best, and that's what we've stuck with our model. Okay, now let's talk about error assessment. Okay, so you can't test the model on the training data set. It doesn't work that way, because then the model already knows. It's kind of like giving it a cheat sheet. However, we do want the model to have all the data that's possible. So we found a little nice solution for this. It's that you separate the data into a test data set and a training data set. So our test data set is 10% of the data, and the remaining is 90%. And you train the model with this 90% training data set, and then you test it with this 10%. But if we only do one of these splits, you're going to get bias, or maybe not so much bias, but it's going to be strongly related to that 10% test data set. So we actually repeat this 200 times, and then from these 200 times, you can take the best error from that. And then in the final model, you can include everything because you have a best idea of what the error of all of the data in is, because you repeated this process 200 times. Good, so that solves that problem. But we have another issue we've got to think about. And that's if you randomly select from an uneven data set, you're going to get an error that's somewhat biased for where you have the highest density of data. So our solution is we can choose the test set on a gridded basis. Now, this isn't super intuitive, so I have a few slides that we can look at to determine that. Okay, so this is our mini calibration data set. We have 30 points here. And as you can see, there's quite a few of them that are right around 5 kilobar. Now, if we extract randomly 10%, which would be 3 points, all of our samples are right around 5 kilobar. So if we do an error assessment on this, this is really only telling us how good our model is behaving at 5 kilobar, really between 4 and 6 kilobar. But it's not going to tell us whether or not your model is going to perform well at 12 kilobar or say 8 kilobar. It's just going to tell you between 4 and 6 how good it's doing. So this isn't so great because it means that your model or your error that you're using isn't the same for all potential users. So you can impose a grid onto this. So we can say it has to take a point between 0 and 4, 4 and 8, and 8 and 12. And as you can see, we have a little bit of a wider distribution of the pressure. But you might also see that you don't have a great distribution of temperatures. We pretty much only have things that are around 1200 degrees Celsius. So of course you'd want to do a horizontal grid as well for the temperatures. So this is what we did. So this is one of the splits of our test and train data set. So the black points are 10% random sampling. The green points are using in gridded sampling. And then the gray is all of our data included. And you can see here that the green points show us the most amount of variability. They seem to be covering what the gray points are the best, whereas our black points are a little bit denser in some of our more dense areas where we have more experiments. Usually this is at 0 kilobar just because there's a lot of experiments that are done at 1 ATM. Whereas in the gridded sampling, we have a lot less of this. So I think it's a fairer version of looking at the error. Okay, now we have a few other things to consider. And so let's circle back to step 5 in my random forest explainer. So this is where we have our little counting statistics that we want to talk about. So we have all of our decision trees, and all of them are telling us different pressures. And so we can plot those up, and then we get a distribution of a bunch of pressures. Now, usually random forest models, when they're in regression mode, they take all of these pressures or variables from their decision trees, and they find the mean. They find the mean of these, and they say that's the true pressure. So this is what we have here, this true pressure, this green line, then the estimated pressure, which would be the mean, is purple. Now, this works great if you have a perfect Gaussian curve like this white one I've kind of drawn on here. But what happens if you get some weird decision trees? Sometimes you get some decision trees that are like dancing to the beat of their own drum. They're living their lives just the way they see fit. And they're a little bit weird. They're a little bit higher. So now we have a little bit of this bimodal distribution. And if we take the mean, it's going to shift further up, and our estimated pressure might be here instead of at the true pressure. Our new estimates are strongly influenced by these outliers. So this is not so great. And maybe using the mean isn't a great option. Okay, so maybe you're thinking to yourself, okay, well, you can just use the mode. That's what they do in classification. Because that just goes by the most number of counts. And in this case, it would be great. It would work just fine. But the mode has a pretty significant issue in that the mode cannot interpolate or extrapolate data. And this is a big issue. So we decided to test this to the extreme to see if it works or not. So we took a test and train data set, we split them. Then after we split them, we took the training data set and we took away everything that was between 5 and 15 kilobar. So you can see there's this gap where the gray line is. And then we took our test data set, which isn't gapped, has all of the data between 5 and 15 kilobar, and we tested it. And as you can see, these green points, these are the mode, there's none between this gap, which means that the mode did a terrible job of interpolating. It cannot interpolate at all, whereas the mean and the median in this case can. And this is something that we have to consider because there are gaps in the experimental data set. And of course, nature is not, discretized, it's continuous. So there's going to be gaps or so-called gaps in nature that we want our model to be able to account for. So instead, we can look at the median. And of course, the median is kind of a nice balance between the averaging effects of using the mean and the bad interpolation of the mode. You could say it's a happy median. It's a nice little joke. So that one works a lot better for us, we think, and it gives us better R-squared values. So the median, I think, is actually the best way to use the counting statistics to get your estimates. Okay, one other thing that we're really excited about with our model is this interquartile range. Now, you might be familiar with an interquartile range. It's just like the two innermost quarters of your curve. And for us, this is great because this is a way that we can understand how confident the model is, whether it really thinks that the estimate it's given you is correct or not. So let's take a look at 3 different examples. So we can look at the furthest to the left here, A. So this one has a true pressure. This is our red line. It's 2 kilobar, and the estimated pressure is 1.7. This is pretty good. It's not so different. And then we can look at our interquartile range, and it's 2.4. This is pretty good. Our model has performed pretty well, and the interquartile range is 2.4. It's reasonably good. The model is reasonably confident in the data that it's giving. Now let's look at B. Our true pressure is 10 kilobar. Our pressure estimate is 10 kilobar. Amazing. We love to see that. And then our interquartile range is 0 kilobar. So the model is really confident in this estimate, which is great because it's estimating correctly. So we can really trust that this region or that this estimate is correct. Okay, now we can look at our last example. So our true pressure estimate in this case is 16 kilobar, but it estimated 19.1, which is not so great. That's about 3 kilobar off, which is, it's not the end of the world, but it's not really good. Now, when we look at our interquartile range, the model has given us an interquartile range of 12.3. This is bad. The model is not confident, even a little bit. It's telling you, I gave you a number because you wanted a number, but I really don't know. So what can we do with this? Well, we can use this as a filtering mechanism. And sure enough, we've tried this and it does work. So you can see in this graph here, we have our estimated pressures on the x-axis and our true pressure on the y-axis. And so these points in green are all of the points in a data set where we've removed anything that had an interquartile range above 7 kilobar. And the gray is just all of the data. So visually, you can already right away see that the green is much better. It's a lot closer to the 1-to-1 line. We're getting rid of some of these outliers that aren't doing so well. It's not perfect, but it's a great solution. We can also see R-squared is much better if we use this filtering. This is something I suggest to all people if they use our model, is to use this interquartile range filtering. We suggest that people use double whatever the standard error estimate is. So in this case, 7 is about that. It's a little bit higher, but it's a great way to try and get like another understanding of how good your data is. Another thing you can also do is you can plot your interquartile ranges on your data, kind of like confidence intervals. So if you have like a bunch of points plotted on like a PT graph, and you have some points that are just around 3 kilobar and they all have tiny interquartile ranges, you can trust those a lot more than say if you had a bunch that were at 5 kilobar but had like an interquartile range of like, I don't know, 2 or 3. So it's a different way of thinking about data. It's a lot more individualized if you want it to be, which I think is a really powerful tool and a powerful part of our method that we're all pretty excited about. Okay, a couple things to talk about before we jump into the applications. So first of all, if you have liquid data, you can also use this model. Of course, liquid data isn't always super easy to come by. Normally it means you need melt inclusions, which are beautiful, wondrous, but also sometimes heartbreaking little blobs of melt in your crystal. But if you do have them, or if you have melt that's on the side of your crystal, it's worth using because it decreases your standard error estimate quite a bit, from about 3.3 if you have no liquid to 2.7. We see the same with temperature. It definitely improves quite a bit. I will give you a quick caveat and then we'll get into the applications. No thermobarometer is perfect and neither is ours. So our calibration data set, while we think is really great, and we're really thankful, of course, to everyone who's made it, all of those experimental petrologists and their hard work, it's not always quite clear from their data what is what. So often, like data from a single experiment, they'll take multiple clinopyroxenes or multiple points within a single clinopyroxene and average them. But then you're not 100% certain if it's actually in equilibrium with the melt. So this is a bit of an issue. We've tried to work around this with an equilibrium filter using a KD filter, but of course we're not perfect in that sense. There's also still gaps in the literature, both in pressure temperature space and in compositional space. If there's any experimental petrologists who are listening to this and you would like to make more experiments with mafic alkali and things, I would be very pleased, but until that happens, this is just a gap that we have in our data set. Additionally, we actually have a pretty high standard error estimate. It's like 3.3, which is comparable to what other thermobarometers are out there, but I think it can be better. I think it's not a problem with the method, but maybe with the data set. I'm always looking at ways to try and improve the standard error estimate. If you have any ideas, feel free to reach out. I would love to hear them. And lastly, there's a little bit of talk in the machine learning communities as to whether or not random forest is prey to overfitting, which maybe it is, maybe it isn't. I'll leave the data scientists to discuss that. Okay, I'll take a look at 2 different applications, and then we'll run through how you can use it, and then we'll be done. Okay, so for my PhD, I look at a volcano, which is called Colle Albani. It is just southeast of Rome, just 20 kilometers to the southeast. You can see there's a nice map of it here. Now, Coleobanny is an interesting volcano because it's dormant, but it's pretty weird as a volcano. So you can see in this like pink color, some of the deposits from the volcano are pretty much like in the city of Rome. Now, this is quite interesting because Coleobanny is a mafic volcano, and it's not only mafic, it's also alkaline. So usually we mentally associate in volcanology, at least, high silica with a higher degree of explosivity. So you can kind of see this here where like some of the big names of the volcanoes that have had big eruptions, they're generally a lot higher in silica than Coleobanny is. We can see it's definitely an outlier. And so part of this is usually a higher silica means a higher viscosity, and then low silica means a lower viscosity, and then lower viscosity is more runny. You can think about Niragongo or Iceland. But Coleobanny clearly hasn't worked in this way. It has this magma that should be low viscosity, yet instead of being runny, it has been explosive and made some large volume explosions. You can see here in this figure, just underneath our feet here, this is where one of these units starts, and it doesn't stop till you get to right about here. This is a huge deposit, and it's just outside the city of Rome. This volcano might be dormant, but I think it offers us with a really interesting question. It's also mafic or alkaline too, and so this is actually why I started looking at this thermobarometer that Mauricio had, because none of the other thermobarometers worked for me. They weren't appropriate calibration ranges, so we turned to find something that would work a little bit better. Okay, so we made this thermobarometer, and now I can apply my data to it. And so we have this here. So this is a pressure on our y-axis and temperature on the x-axis, and of course a proxy for depth on the second y-axis. So I'll give you a second to look at that while I drink some water. Okay, so we can see here we have this cloud of pressures that's kind of right around 2 to 4 kilobar. And this is actually great because Bianchi et al. In 2008, they did a geophysical study, and they found a limestone layer here, and they found right below this limestone layer, they have something that they suggest is a old magmatic reservoir. So that's good. That lines up pretty well. This makes sense. If they're saying that there was a reservoir there at some point, it makes sense that some of our data should be coming from this. But actually, in reality, when I first looked at my data, because I do some mineral chemistry stuff as well, I was actually not pleased with these results because, as you can see, we've color-coded for magnesium number, and some of our magnesium numbers from our clinopyroxenes are really, really high. And so when we look at it in combination with chrome content, we can see that some of these clinopyroxenes are pretty much in the same chemistry as clinopyroxenes that come from Harzburgidites, peridotite, clinopyroxenites. These are melts that you would imagine would be in equilibrium with the mantle. But the mantle is not at 2 kilobars. The mantle is, a little bit deeper. So this is why when I first saw this, I was actually quite concerned, and I thought the model wasn't working. But then we stepped back and took a little bit of time thinking about the pathway of the magma and the potential pathways that it could take. So one of the things you can think about is the liquidus. So where do the crystals actually first crystallize? And so usually you can use a software called Melts, which maybe you're familiar with, which is a great software at looking at the liquidus, except for it doesn't work with alkaline and mafic melts. So once again, I go back to the drawing board and you go old school and take a look at some phase equilibria experiments. So I've plotted them out here. So you can see that if it's all purple, it means it's glass. And then if you start to get these colors, you get some crystals. And so you can pretty much see where we could draw our liquidus, where on one side it's glass and on the other side we have crystals. And you can see there's a little bit of a kink here. All of these are hydrated. So this is the wet liquidus. That's why we have a little bit of the kink there that we can see, at least with these. And then we can even just draw the liquidus on here. We've added a shaded region because not all of these are quite the same. There's some overlapping ties because some of them were done at different gaseties or water or carbonate contents. So we can take an adiabatic ascent path starting from about 1250 degrees Celsius and 10 kilobar, and just going up. And we can see it stays just to the right of our liquidus. It just kind of flirts with it. It doesn't quite cross it until boom, it gets to the wet liquidus, and then it crosses. And then we can see if we overlay that on our data, this works out pretty well. We have this cloud of data right where we could imagine our adiabatic ascent crossing the liquidus. This is a great way we can kind of understand what's happening in this system, at least from the pressure point of view, and kind of start to think about more than just what the pressure and temperature is, but how did these crystals get here, and looking at the chemistry and try to understand where our magma actually came from. Okay, so let's take a look at another example. I'll show you an example from my colleague, Oliver Higgins, Dr. Oliver Higgins. He just defended his thesis last month, and Oliver looks at St. Kitts, which is an island in the Caribbean Sea, and he looks at specifically the Mansion series. So Ollie one day was taking a look at his plagioclase that he has in his data, and he found that progressively from old to young, he finds the plagioclase anorthite content increases. You can see that in these curves here, these nice little rainbow curves. The anorthite content increases. However, if you look at the bulk rock, so these kind of gray dots you see here, it's pretty invariable. It like stays pretty much the same. Why? What's the change? What's happening here? I'll give you a hint. We're talking about thermobarometry, so it's going to be either pressure or temperature. Okay, let's take a look. So Ollie did some thermobarometry on both clinopyroxene and also amphibole, and he found the pressure doesn't change that much. You can see it here in this first graph. It's kind of invariable. It flip-flops back and forth, but not so much. But when we look at temperature, it's quite clear here that as you increase in stratigraphy, you also increase in temperature. And if you look at the anorthite content, you also increase in your anorthite content. Ollie was able to look at the anorthite content of a completely unrelated mineral and answer that with this thermobarometer, which I think is a really, really cool application. It really allows for you to kind of postulate what other questions you can answer with the thermobarometer. Now, of course, he also did amphibole thermobarometry. So if that's something you're interested in, you can check out his paper that was accepted in early 2022. Yeah. And he also has a chemometer. So that's essentially using the same methodology, but instead of searching for pressure and temperature, you search for melt composition. So if you want, you can check it out. It's a great paper. Okay, so now, if you are interested in a random forest thermobarometer, of course, you could check out the paper, but one of the easiest ways you can access it is go on GitHub, and we have a non-static repository there. So that's like the most updated version of the code. As issues come about, this is where they will get resolved, and we'll like try to keep everything updated there. So we have two versions of the code. Both of them are written in R. The first one is the choose your own adventure. This one allows you, This one allows you to make the model, to adjust parameters and inputs. So if for some reason you wanted to filter the data set, or you wanted to extend it to pressures past what we've suggested, or only look at smaller pressures, you can do that there. It requires a little bit more coding experience. There's a set of, I think it's 8 different scripts that you use to make the code. There's also the plug and play version. This also requires R, but it has minimal coding. It's static state, you can't change it too much. It's a little bit of a black box, but for people who maybe aren't interested in coding and don't know R, it's a good option for them. In both instances, in these zip files, there's an input data folder. This is a CSV file, and basically we suggest that you just change the rows here. You keep the first column, or the first row, the column headers the same, because that's what the data is reading. It needs to have this .cpx, otherwise it won't work. But you can just copy and paste basically from 2 down your data in here. Now, I will say there's one thing that has happened. Just 2 months after our paper got published, the package that we used got archived, which was so unfortunate. And I'm still trying to figure out if we can unarchive it somehow. But you can still use it, no problem. It just requires an extra step. So basically, if you're going to install the package extra trees, and it tells you it gets mad, you just have to download the archive package from this website and then run this line of code and just change users can see downloads to like wherever you have this saved. If this is an issue that you face, if you go back to like the GitHub page, there's a little thing called issues up here, and you can click on that. And then there's a little thing called extra trees is archived. There's this comment, but of course you can also email me. I'm really happy to Zoom with anyone to try to get this fixed for them. I'm sorry, it wasn't something that I was in control of, but hopefully people still use the code anyway. So with the plug and play method, you can just select whether or not you have liquid data or not, and then basically select everything and run it, and then it should work. Okay. So in conclusion, our thermobarometer, it's a data-driven approach to clinopyroxene thermobarometry. It allows you to have some individualized estimates and a really robust error assessment. There's a possibility to easily change and evolve the model with time. And if that's something you're interested in, please reach out. We're always looking for ways to improve our model. And it has a wider range of applicability in pressure, temperature, and compositional space. So thank you so much. And if anyone has any questions, I would love to hear them.
Okay, great. Okay, let's take questions from participants. So feel free to open your mic to ask a question directly, or you could also leave a message in the chat and I can read your question on your behalf.
Hi, Corin. Thanks for a very interesting talk. I'm not a geochemist, but I'm always interested in machine learning. So that was the part that I was very interested in. I think like you and your group, a lot of us are also really interested in the use of the IQR. Because I mean, personally, I really like any kind of model that can output any kind of uncertainty estimate. It's basically the other 50% of your prediction. You must have an uncertainty estimate. So it's super cool to see that you're able to get something like that. So you hinted at some ways you can use the uncertainty to kind of investigate which data are more reliable than others. Is there a way to use it to kind of reverse engineer like what the input data are and any commonalities between bad input data or really large uncertainties in those predictions?
Yeah, so we've discussed this a little bit of whether or not we should run our calibration data set through once and then filter out all of the bad, make the calibration data set, make a model, and then test the entire calibration data set. And then anything that has a really high IQR, remove that from the calibration data set and then try again. So it's almost like doing an iterative filtering. We've discussed that, and we might end up doing it because like this is the thing is I think it's like if you put bad data in, you're going to get bad data out. So this is potentially a great way of figuring out how to better filter our calibration data set. So yeah, that's what we've been thinking of now. But if you have any suggestions, I would love to hear them.
Not at the moment I do, but if I stew about it a little bit more, maybe. Yeah, another thing, I'm also not super familiar with random forest, but is there a way you can like use those S scores that you calculated to kind of go up the tree and see which leaves have higher variance, and those are associated with certain inputs or certain features, and what is it about those features that can cause a high variance in the S score?
Yeah, generally, like you can look at the importance of different elements. Like that's something that random forest has. Actually, the package extra trees doesn't allow you to do that, which is a little bit annoying, but we've looked at it with random forest. And this is an interesting thing because it actually agrees pretty well with what the like thermodynamics says. of like which elements are more likely to control the pressure. So you can do that. As far as looking at the individualized scores, we haven't done that, partially just because I think like it's so random where it chooses where to do the split. That's part of using extra trees. In random forest, it always splits in the middle, but extra trees, it does a random split. So like it might split your silica content at like 40%. So of course, like it's not going to get as good of a variance there as if you split at like 50% or 60. So we haven't looked at individualized at that, but it's an interesting idea. I'll think about it.
Right. Cool. Oh yeah. Thank you.
Yeah, thanks.
Okay, there's a question in the chat asking by Arkayoti from Indian Institute of Technology, and he's asking about whether changes made in multi-component fluid parameter X change the model error estimations much.
So I think if I'm correct, this question is asking whether or not if you add liquid data, if it makes the error better or not, which it does, unless you mean adding. Can you clarify what you mean by multi-component fluid? Like, do you mean like the melt composition, or do you mean like other fluids? Because we don't have any other fluids like water or CO2 in our model.
I think our conversion means the melts, the magmas.
Melt, yeah. Okay, so if you add liquid data, it actually makes the error a lot better, because of course, like the composition of the clinopyroxene is a function of the melt that it comes from. So of course, when you have the melt data, it makes it a lot better. And in our case, for the pressure, the model error goes from 3.3 to 2.7 kilobar. So you get about half a kilobar of better error estimates. I hope that answers your question. If it doesn't, please let me know. Okay, cool, great.
Okay, next question, please. Okay, I have a question that I think you speak a little bit fast on it. I didn't follow very well. On that portion where you talk about using the I say the different chromium concentration, etc., and then trying to tell the source of the magma. So could you clarify that part a little bit, because I was a little bit lost on that part.
Yeah, okay, so this is work that like I'm currently working on. So usually you associate usually clinopyroxenes don't have a ton of chromium in them, unless they've come from being in equilibrium with a mantle source. So like clinopyroxenes that come from like a Harzburgite, a peridotite, or a clinopyroxenite, usually those are the ones that have high chrome and high magnesium number. Like these are like igneous rocks that you don't often find in volcanic systems. Usually volcanic systems have a lot lower like contents of chrome. Usually normally it's like the minor, you don't have a full weight percent. This is quite a bit. Usually chrome you need to measure with like the laser because it's on parts per million levels. So the fact that we have really high chrome indicates to me that at some point this magma should have been much deeper than just like shallow crustal and should have been in equilibrium with the mantle at some point. So this is why when we first looked at this, I was like quite shocked. Even like these magnesium numbers are really, really high. It's pretty hard to get those. So this is why like when I first saw this, I was like, oh no, this is not good. But of course, if you look about it with this like adiabatic descent, it can still come from deep. You just need to make sure that you're not crossing the liquidus. So one of the ways that you don't cross the liquidus is actually by ascending really rapidly. Because when you get higher up, usually like if you follow the geotherm at lower pressures, you have lower temperatures. The only way that you don't like stall and then cool is if you ascend quite rapidly, which is actually what we think is happening. We think that there's pulses of magma that are coming from depth quite rapidly that are stalling in this like lower reservoir, which is actually why we see this variation of temperatures from 800 to 1200 degrees Celsius. I think this is showing us this accumulation of magma at this shallow depth that which would have come from much deeper, stalls here, accumulates and accumulates and accumulates. And so these crystals are crystallizing at higher and higher temperatures until we get potentially a final one that kind of sets everything off and triggers the eruption. And then like consequently, we get a caldera collapse. Does that answer your question?
Okay, so for that, then I would expect that the possibility we could measure, for example, hydrogen diffusion profile, and that could clarify quantitatively tells us that how fast does this let's say
the ascent rate, yeah,
eruption, the eruption that it goes. So that's the only thing that people do, for example, for kimberlite related. Another part that I think is that with some isotopic evidence that could further confirm the metal source origin. Metal derived magma involved in the magma that you finally see.
Yeah, so actually, so with the hydrogen diffusion, that's like the next year of my PhD, that's my next step. But we've actually done some of the isotopic stuff looking at that. Because actually one of the big things in the literature is people suggest that the weird eruptivity of this volcano is because there's this limestone layer. They think it's carbonate assimilation, and increased carbonate means more CO2. More CO2 potentially means more explosive. But we took a look at some of the strontium neodymium isotopes of some of these clinopyroxenes, and it shows that you have to have some sort of mantellic source. We suggested from like a metasomatized mantle, but you can't get the signatures that we're getting without some sort of metasomatized mantle source. It just doesn't work with a depleted mantle or with carbonate assimilation. So yeah, it's been a fun thing to work on. So yeah, both of those are things we've been thinking about. Thanks.
Okay, thank you. Next question, please.
Hello again. I'm going to jump in again because while I have you as a resource, the number of trees you said did not really affect the accuracy of the prediction, right? Does that have any effect on the IQR? Like, does increasing or decreasing the number of trees affect that much?
Wow, we didn't look into that. That's something to look into.
Okay.
I would assume no.
Yeah.
Because it doesn't affect the residuals, but I'll look into that. That's an interesting idea.
Okay, cool. and I guess related to that, you made a comment that some people in the data science community are saying that the random forest may overpredict. Do you have any sense of what they're talking about? Like, well, how could it overpredict?
Yeah, overfitting is a thing that they talk about a lot, which yeah, I feel like I'm not good enough at machine learning to be able to fully have a great answer for you, but it's something that's debated. Some people say that overfitting is definitely something that happens with random forest. Some people say it doesn't. I think it kind of depends on what you're doing with your data. And I do also think, like, even if there is some degree of overfitting, it still is it's still a good model. It's a good option for us. I suppose there's maybe some other machine learning methods that you could look into, like GAN or neural networks, but I don't think we have enough data for neural networks, and I'm not sure about GAN. Something to think about, but yeah, I can't give you a great answer, sorry.
But with these trees, can you control like the depth of the trees? And so like each way you could make each individual tree, I guess, a weaker machine learning model, so that when you then combine them as an ensemble, they should potentially overfit less. That would be my first instinct.
Yeah, you might be able to control depth of trees. Usually the model just goes until it can't split anymore. So it like
Oh,
it
okay.
splits the data set until it arrives at a single point.
Okay.
I don't, you could choose a little bit more of the splitting. You could like affect that a little bit more. Like one of the things you can do is like in extra trees, you can increase the number of cuts. So like I explained the M-try as a binary cutting, but you can actually like you if you think about this, you can have yes, no, but you can also have maybe as an answer. And so you can do that, and in that case, usually you get deeper trees. We did some testing with increasing the number of cuts, and we found it doesn't really fix anything. It just makes the model a lot slower, like a lot slower. So for us, we decided it's not worth it, but it's something that like people could look into because that would like also increase some degrees of randomness, which might make it so you have less overfitting.
Right. Thank you. That's very useful, practical information.
Yeah.
Okay, there's that question in the chat. So asking about the change of the liquidus, because that thing that liquidus that you plotted seems like the hydrous one, but it maybe we change much after the carbon simulation from limestone.
Yeah. Okay. This is a. Okay. You're saying something? Okay. Yeah, so the liquidus we have drawn here, like, actually you want to see the liquidus that I've drawn. It's actually just like hand sketched because melts doesn't work for it. So this is our best guess. And these experiments, some of them are carbonated, some of them are not. But also like what you've said, the liquidus will change much deeper because carbonate and carbon dioxide exsolves at a much deeper depth than water does. And as far as I know, when it exsolves, it doesn't make that much of a change in what the liquidus is doing. It's water that's the big one.
Okay, I think that's great for the webinar today. So Corin, please stop sharing your screen, and then everyone, could you open your video and show our appreciation for our speaker today so that you can see everyone today. So everyone, please open video, and then we could finish the meeting in 30 seconds.
Thanks so much for having me. It was a great opportunity. I really enjoyed giving this talk. It was great.
Yeah, thank you for your time.
Great. I'll be heading out. Thanks again, everyone. Bye. Have a great day.